Welcome to class number 16 of transport phenomena in mesoscopic and nanoscopic systems. So we were discussing about Green's functions, and this is basically the last equation which we derived. Okay, so we'll like to discuss more about this equation and how do we basically go from this kind of theoretical formulation into the current flow. So we'll discuss about that, but before that let us discuss the concept of basis transformation, which is kind of important in understanding some intuitive aspect of this course. So let us consider this coordinate system transformation. So let us consider this as the x-axis and this as the y-axis. And now if I actually take a new coordinate system which is inclined at 45° to the x-axis, so I can get two new axes here. Okay, so this x and y are the axis of my old coordinate system, and I am transforming this into a new coordinate system which are inclined at an angle 45° to the x-axis. So these are the two new axes which are inclined at an angle 45° with the x-axis, and we just call them these two new axes as x dash and y dash. And we can say that any point on the x-axis, okay, any point on this axis over here, okay, so this can be written as x dash. What is x dash? So this is basically 45° to the x-axis, so it must be equal to x divided by root 2 plus y divided by root 2, so cos 45° and sin 45°. Okay, so similarly this other coordinate axis, this y dash, this has to be equal to y dash equal to minus x divided by root 2 plus y divided by root 2. So we can basically write it in a matrix format, and we can write it as x dash y dash equals to some matrix C. So C is a matrix times xy where this matrix C is basically given by 1 by root 2, 1 by root 2, minus 1 by root 2 and 1 by root 2. So we have a relation between the old coordinate system and the new coordinate system. Now we can also invert the relation, and we can also write it as x y equals to C inverse x dash y dash. So we have a way, okay, so we have a way of moving from one coordinate system to another. The representation is different, but note that if I have a point xy over here, we can readily go to the coordinate system x dash y dash and vice versa. We can move between the two coordinate system, but the point is basically the same in 3D space, or the location of the point is basically the same. It's nothing that is changing about the point. It's only that we are having different way of representation in the xy coordinate system and in the x dash y dash coordinate system. Okay, so the relation between two systems or two spaces or two coordinate systems is basically given by this matrix C over here. Okay, so in the same way, when we have physical functions, we can basically break them down into basis vectors, and there can be multiple basis vector. For example, a function in the real space can be represented in terms of the coordinate system x, y, z, or it can also be represented in spherical coordinate r, theta, phi. Okay, and it can also be represented in the reciprocal space in terms of kx, ky and kz. So these two are basically related by a Fourier transform, this xyz and the kx, ky, kz space. Fourier transform or Fourier series in case of periodic functions. And then we can also have this kr, k theta and k phi, and these two are again related by this Fourier transform over here. So note that the function is basically the same. Okay, so the function is basically the same in these two cases, but it's only different way of representation, or in other words, different space of representation. So if I go from xyz to this space r theta phi, or if I go from this space r theta phi to this space xyz, my space is the same, but I am choosing different coordinates to represent a function. So I am transforming coordinates here. So this is kind of this is also a kind of basis transformation, but this is a basis transformation in the same space basically. And then we can represent this function in xyz, or we can also represent the same function in this kx, ky, kz. So kx, ky, kz, as you already know, this is the known as the reciprocal space. So if xyz represents the real space, this kx, ky, kz basically represents the reciprocal space, and these two are basically related by Fourier transform. So these two are representations of the same function in different spaces. Okay, so these are basically representation. This basically represent basis transformation between different space. One is the kx, ky, kz space, which in case of wave functions are known as the momentum space, and one is the xyz space, which is the basically the real space. Okay, so basis transformation in different space. Okay, so just like before, just like in this case, we basically have a matrix C which connects two different coordinate systems, or which helps us move from one coordinate system to the other coordinate system. In case of this transformation between two different spaces, or transformation between two different basis sets which represents different spaces, we also have this matrix C. So just like this one, so let me go to this previous page. So just like this new basis vector here, this is not a vector, but this is kind of coordinate, but I could have written it in vectorial notation also. So this new coordinate is written as the sum of the old coordinates in the old coordinate system. So here also I can represent the new basis vector in terms of the old basis set. Okay, so let me assume that phi new represents new set of basis functions in which we like to represent the wave function or something, and phi old is basically our old basis set. Okay, for example, phi old may be the real space basis set, and phi new might be the momentum space basis set. Okay, or this phi old might be the momentum space basis set or the momentum space eigen functions, and phi new might be the eigen functions of the Hamiltonian itself. Okay, so we can transform from one basis set to another, and ultimately nothing changes because we are representing the same function. It's only the space that is changing, or it's only the basis set that is changing. Basis sets are kind of like the components functions, or the components via which we would like to represent a function. Okay, so this phi nu, so phi nu is basically a set, and we take the ith component of this basis set. So this is equal to summation over m c mi phi old m. Okay, and we can write this old basis set in terms of this we can represent this new basis set in terms of the old basis set with the help of this matrix C. So this phi new and phi old would normally be functions of the real space, so the real space coordinate system. So these are the functions of R basically, although it's not necessary, this is the kind of general case. So I'll write this R here. Now any function fr can be represented both in terms of the new and the old basis set. So we have this as summation over m am phi old m, and this is also equal to summation over I bi phi new I. So this will in general be functions of R. So I will write this R over here. So now this is equation number 1 and this is equation number 2. So now by comparing these two equations over here, what do we get? So in this equation we can replace this phi nu I by this equation. Okay, so in that case what do we get? If R is summation over I bi phi new I summation over I summation over m bi cmi phi old m. Now this fr, this is also equal to summation over m am phi old m. So now this m and I, these are two independent numbers, independent indices. So I can basically interchange this order and I can write it as summation over m summation over I cmi bi phi old m, which is equal to summation over m am phi old m. Now since this is true for any function, okay, this is true for any function fr, this basically means that the coefficient of this basis in these two equations must be the same. Okay, otherwise this should not be true. So we get that am, which is basically the coefficient of this phi old m over here, is equal to summation over I c mi bi. So this means that if I form a row vector A with the help of this coefficient, if I form this row vector A where A is equal to A1, A2, A, M and so on, if I form a row vector A, and if I form a row vector B, where B is equal to again B1, B2, Bi, and so on, in that case this A vector is related to this B vector by again this matrix C, where C was the transformation matrix which connected between two basis vectors. Okay, so C was basically this transformation matrix which basically connected the two basis vectors, or which transformed the old basis vector into the old basis set into the new basis set. Okay, so remember that A and B are the coefficient of the basis set for representing the same function fr over here. Okay, so this B is basically the coefficient of new basis set and A is the coefficient of old basis set. So note that when we talk about transformation between the basis vectors, so this old basis set is basically transformed into this new basis set by this matrix C over here. Okay, so when it comes to the coefficients, okay, when it comes to the coefficients of the functions, that is this A's and B's, it's kind of the reverse. So here this matrix C is basically multiplying this old basis set to take it to the new basis set, and when it comes to the coefficient, this matrix C is multiplying the coefficients of the new basis sets for a function and transforming it into the coefficient of the old basis set. Okay, now remember that I also told that how we represent an operator in matrix format basically depends on the what basis sets you are using. Not only in matrix format, but how we represent an operator basically depends on what basis sets we are using. Okay, for example, if we use the eigenstates as basis, if we use the eigenstates of Hamiltonian as basis, then the Hamiltonian would look diagonal. So H would basically have this form: E1 0 0 0 0, E2 0 0 0 0, E3 0, and so on and so on. Okay, so this is the representation of the Hamiltonian when the basis is the eigenfunctions of the Hamiltonian itself. So when the basis is the eigenfunctions of the Hamiltonian, then the Hamiltonian would be a diagonal matrix. Okay, on the other hand, when we use the basis set corresponding to the eigenstates of the position operator, in that case the Hamiltonian looks tridiagonal. So in that case the Hamiltonian has this form. And so on. So this is the case when we take our basis set as eigenstates of the position operator. Okay, so how we represent an operator basically depends on what basis set we are using. Okay, so any operator, as we know that any linear operator can be represented in a matrix format. Okay, So that operator representation would basically change depending on what basis we are using. So let us see how it would change. So let us consider this element, this matrix element. So transformation of operators when you go from one basis set to another. So let us consider the old basis set and an operator A in the old basis set, and we take one particular element of this operator in the old basis set. Okay, so we take the ith and the jth element of the matrix. So this is equal to phi old j, the actual operator A, and phi old this is I, phi old j, and this we have seen earlier. Now how would this operator, or how would this particular element of this operator look like in the new basis set? So a new ij is basically equal to phi new I, this operator A, phi new j, and then we can expand this. We use the relation phi summation over p, let us write it as m, summation over m phi old m we write it here so this is a Bryan-Kate notation, and summation over m, this is equal to the identity operator which we represent by 1, not a 1 in numerical sense, but this is the identity operator. This is a matrix basically, and that's why I have written this double line over here which represents the identity operator in matrix format. Okay, so this is basically equal to let me write it here, phi new I, and then we introduce this summation over m here, phi old m phi so this summation should be outside actually, so summation over m phi old m phi old m a, and then I again take this summation over here, summation over n phi old n phi old n, and then phi new j. Okay, so let note that this is equal to the identity operator, and this part is also equal to the identity operator. So basically these two along with the summation, so this is equal to the identity operator. So this two does nothing as far as the value of this term is concerned, because identity operator basically multiplies an operator or a number and it gives you the same thing basically, not a number but identity operator basically multiplies another operator and it returns you the same operator. Okay, it's the identity matrix basically. So Now to proceed from here, let's note that what is this term? This term is equal to the element a mn in the old basis, so we call it old. And then what is this thing over here? This is a number because this is an inner product between phi old and phi new. So this is equal to C j n complex conjugate. And what is this thing? This is equal to CMI. Okay, and we have this summation over here, right? So this summation can actually be taken out because it does not impact this expression. M and N are independent numbers, so summation over M, summation over N. So this is actually Cnj, so Cnj, because this is transforming this nth component into this jth new component. So this is equal to Nj star. Sorry, there is a mistake over here. This should be in complex conjugate actually, because we are basically here I am making this complex conjugate, so the coefficient should be also in complex conjugate over here. Okay, and not in this case. Okay, so now there is a beautiful way of representing this entire double summation. So Aij, so let me write the complete thing over here. Aij new is equal to summation over M, summation over N, Cmi star Cmn old and Cnj. And there is a beautiful way of writing this in matrix format. So A in the new basis representation is equal to this matrix C dagger. Dagger is basically the complex conjugate transpose of the matrix A operator in the old representation or in the old basis, and then this matrix C. Okay, so an operator basically transforms like that. Now when we transform from one basis set to another, we generally have a kind of transformation which is known as unitary transformation. Okay, so unitary transformation basically comes from the fact that wave functions need to be normalized. Whether you are using one basis set or a different basis set, so wave function should be normalized. So which basically means that if this fr, if fr represents a wave function, and this is equal to summation over m am phi old m, and in the new basis set it can also be represented as summation over I bi phi new I. Then since the wave function is normalized, so this inner product of fr with itself should be equal to 1, and these are the basis sets, so their inner product is also 1 because the basis sets are generally chosen to be orthonormal basis set, although it's not important that they are always chosen to be orthogonal sets, but they should at least be normalized. Okay, so this basically means that a summation over m a m star am phi old m is equal to summation over I bi star bi phi new I phi new I. So this basically assumes an orthonormal basis set. Otherwise there would be inner product between m and n. Okay, so this assumes an orthonormal basis set. So let me just border it here. So this basically means that since this is equal to 1 and this is also equal to 1, this thing basically means that summation over m am star am is equal to summation over I bi star bi. So in other words, we can write this as a dagger A is equal to B dagger B, and remember that B is basically the coefficient of the new basis vectors. So we have A dagger A is equal to B dagger so this B is related to this A by this transformation matrix C. So we can replace this B over here by this A dagger C dagger, then C A. Now since this is true again for any vector, any A vector for normalized wave functions, we would be getting this C dagger C equals to the identity matrix. Okay, so the transformation given by this matrix C, the basis transformation, is basically a unitary one. So C is basically in that case a unitary matrix, and transformation given or represented by unitary matrix are known as unitary transformation. Okay, so the transformation between two spaces in this case or this kind of cases are known as unitary transformations.